Welcome to the deep dive. Today we're looking at your sources, pulling out the key ideas on, well, a really interesting topic. Adapting these huge AI models efficiently.
That's right. We're focusing on something called parameter efficient fine-tuning, or PEFT, and specifically one method called low-rank adaptation, LoRA.
Yeah, these massive models are amazing, but tweaking them fully, for specific jobs, that takes just a ton of computing power and memory.
LoRA offers a clever way around that. It adds these small, trainable, low-rank matrices. They sort of guide the model, but the original huge set of weights stays frozen, so it's much, much more efficient.
Okay, but the sources you sent over point out a snag with the standard LoRa approach. It helps, sure, but apparently performance can sort of stall or even drop if you try to make those adaptation matrices bigger using higher ranks. Doesn't quite get you to the same level as full fine-tuning.
And that's the core puzzle for this deep dive, isn't it? Figuring out why LoRA hits that ceiling and exploring this new approach from the sources that tries to break through it.
So what's the main reason identified in the material for this limitation?
The term they use is gradient entanglement. It sounds complicated, but the idea is that LoRa's structure can let unrelated input signals disproportionately affect the learning, especially these things called outlier channels.
Outlier channel.
Yeah, input channels that just have really, really high activation values sometimes. They can kind of dominate the process.
All right, let's unpack LoRa itself a bit more then. How does it actually work under the hood?
Okay, so you start with your big pre-trained weight matrix. Let's call it W0, like in the sources.
Right.
Then LoRa brings in two much smaller trainable matrices, A and B,
Yeah.
with low rank R. The actual update or adjustment R is basically calculated as B times A transpose. Sometimes scaled, but let's keep it simple for now.
So the model's output, Y, is what it would normally output, W0 times X plus this new adjustment, R times X?
That's it. And the crucial part is only A and B get trained,
Yeah.
not W0. That's where the massive parameter saving comes from.
Okay, that makes sense. But why does increasing R the rank sometimes hurt performance? More capacity should be good, right?
Well, it's counterintuitive. The sources suggest LoRa's gradients, because of how R is calculated, are sensitive to the whole input space at once. And those outlier channels we mentioned.
The ones with high activation.
Yeah. When you increase the rank R, you're sort of increasing LoRa's sensitivity. And if you have a few very strong outlier signals, they can end up overwhelming the learning update for the entire adapter. It drowns out other potentially useful signals.
Okay. And how's that different from just fine-tuning the whole model?
With full fine-tuning, if you have an outlier, its effect is more localized. It mainly impacts the weights directly connected to that specific channel.
But LoRa spreads the impact.
Exactly. In LoRa, an outlier can heavily influence the gradient update for the entire B matrix. This distorts the whole update, making it hard for LoRa to really mimic the detailed changes that happen in full fine-tuning. The sources even point to an example in LAM A3.18b, where they see this channel imbalance in action.
And this gap, this deviation between LoRa's gradient and the ideal full fine-tuning gradient, it gets wider as the rank R goes up.
That's what the analysis shows. Higher rank LoRa becomes more susceptible to these outliers, not less. That seems to be why performance can plateau or even drop. It's like the structure itself makes it vulnerable to being hijacked by a few loud inputs.
Okay, so that sets up the problem nicely. How do the sources propose fixing it? You mentioned GraLoRA.
Right, GraLoRA, Granular Low-Rank Adaptation. The core idea is pretty neat. Instead of one big LoRa adapter, you split the main weight matrix, W0, into smaller chunks.
Like tiling.
Kind of, yeah. Imagine a grid, say K by K blocks.
Okay.
And then each of these smaller subblocks gets its own independent LoRa adapter, its own A and B matrices. Figure 1 in the sources gives a good visual for this.
You're breaking the adaptation task down.
Exactly. And this K parameter, the number of splits per dimension, you can tune that. If K1, it's just regular LoRa.
Makes sense. What are the upsides of doing it this way, this granular approach?
Two main things jump out from the sources. First, more expressivity. Having separate adapters lets the model learn more specialized things in different parts of the weight space, like having different specialists focus on different areas.
And the second, it must relate to the outlier problem.
It does. Robustness to input outliers. Because the gradient updates are now localized within each subblock's adapter, an outlier channel only strongly affects the adapters that directly interact with it.
So it doesn't mess up the learning for the whole matrix anymore.
Precisely. It contains the blast radius, so to speak. The overall gradient distortion is much lower, preserving the balance between different input signals better. It prevents one noisy input from derailing everything.
Okay, let's get slightly more technical on GraLoRA. How does the overall update work?
The total adjustment, R, is basically the sum, or concatenation, of the adjustments from all these little blockwise adapters.
Mm.
And the rank for each small adapter, it becomes R divided by K. So the original rank R gets distributed among the blocks.
And there was something about sparse matrices.
Yes. Figure 5 shows you can also think of GraLoRA as multiplying two large, sparse matrices called GraLoRA and GraLoRA. This view helps analyze the overall capacity.
Right, the effective rank. What happens to that?
This is interesting. The analysis suggests that the effective rank of the combined GraLoRA adjustment actually becomes K times R.
So wait, by splitting it, increasing K, you actually increase the overall representational power for the same starting R.
Under certain conditions, yes, it's a key finding. So GraLoRA, by being granular, can actually express more complex adaptations than standard LoRa with the same initial rank budget. Table 4 highlights this.
So back to the outliers. With GraLoRA, their impact is limited to just the adapters they touch.
Essentially, yes. If an outlier hits input channel I, only the K adapter pairs along that row or column intersection are significantly affected. The gradients for the other adapters stay much closer to baseline levels.
Which sounds much more like how full fine-tuning would handle it.
It does. It mimics FFT more closely in that regard. Figure 6 and Figure 3C. And the sources show this reduced gradient deviation and contained outlier influence compared to standard LoRa.
Okay, sounds promising. But are there any trade-offs? What about computational cost or memory?
Computationally, the overhead is very similar to standard LoRa, still in the order of OR M plus NT. Appendix C breaks this down.
Yeah.
Memory-wise, there's a slight increase during training because the intermediate stuff gets K times larger.
Ah, because you have K sets of adapters working in parallel.
Sort of, yeah. But the sources indicate this increase is pretty marginal in practice, especially since R is usually small compared to the matrix dimensions. And you can use techniques like gradient checkpointing if needed. Table 1 shows negligible memory bumps.
And choosing K, can you just crank it up really high?
There's a balance. If you make K too large, the rank per block becomes tiny, limiting what each block can learn. The sources suggest keeping the block expressiveness, roughly a rack above a certain threshold, maybe around 8, works well. Figure 8a shows experiments varying K, confirming this diminishing return.
The sources also mentioned a hybrid GraLoRA. What's that about?
Yeah, that's for situations where the starting rank R is quite small, maybe 16 or less. In those cases, regular GraLoRA might not give huge gains.
So the hybrid mixes things up.
Right. It combines GraLoRA with a bit of standard LoRa. Essentially, some parameters get shared across blocks, bringing back a bit of the global LoRa structure. Figure 7 illustrates it.
And is there a sweet spot for this mix?
Empirically, yes. The results suggest that for these low ranks, dedicating maybe up to half the total rank budget to the standard LoRa component helps. But for higher ranks, going full GraLoRA seems better. Figure 8b shows that trade-off.
Okay, let's talk results. Did GraLoRA actually work better in practice? How did it do on tasks?
The experiments look pretty positive. On code generation, using HumanEval plus us, GraLoRA consistently beat standard LoRa and a couple other PEFT methods they compared against across different ranks.
Any specific numbers?
Yeah, particularly at rank 64 and 128, the improvements were quite significant, like a plus 2.4% jump in task at 1 at rank 64, and a big plus 8.5% at rank 128. And hybrid GraLoRA did well at the lower ranks, as expected. That's all in Table 2.
What about other types of tasks, like reasoning?
Similar story there. They tested on commonsense reasoning benchmarks with various models, Quinn 2.5, LeMay 3.1, and GraLoRA generally outperformed the baselines again, showing better average accuracy. Table 3 lays that out.
And you mentioned some other analyses supported these findings.
Correct. The ablation studies, like the K-sweep and the hybrid ratio sweep in Figure 8, helped justify the design choices. And they looked directly at gradient distributions, which visually confirmed in Figure 9 that GraLoRA localizes updates and mitigates that entanglement issue. Plus, the rank analysis in Table 4 backed up the idea that GraLoRA effectively increases adaptation capacity with K.
So wrapping it up, GraLoRA seems like a solid way to push past LoRa's limitations, especially if you need higher performance and are willing to use larger adapter ranks.
That seems to be the main takeaway. By making the adaptation granular, breaking it into these blocks, GraLoRA manages to sidestep that gradient entanglement problem, especially the outlier issue.
Right.
This lets it behave more like full fine-tuning and leads to those performance improvements we saw, particularly noticeable at higher ranks in demanding tasks like code generation.
The key insight really feels like understanding why LoRa struggled that gradient dominance and then finding a structural fix, the blockwise approach, that directly addresses it.
Well put, and it definitely makes you think, If uniformly splitting the matrix works this well, what could you achieve with perhaps smarter, more adaptive ways of partitioning the weights during fine-tuning? That's maybe something for you, the listener, to ponder as this field keeps evolving.